All right, so what we want to do now with logarithmic functions is we want to make graphs of them. And maybe not make graphs that you would use in a publication, but graphs in the sense that you can visualize what the function does. So if you're anticipating, what kind of changes you have as you change x, being able to visualize a graph is good. Okay, so here's a graph of the log base 2 of x. And all the log functions have this basic shape. Remember, just like the exponential functions all were shaped the same, it's a question of how fast do they go up to infinity, how fast do they go down to 0. And so, as you would expect, you have the log base 2 of 1 is 0, and then the log base 2 of 2 is going to be 1. And so we have those key points in there. And you can see those 2 points are going to be the points that kind of guide us on how we're going to do our graphs. The other thing that's to note is the vertical asymptote. Remember that in our expression of the log base anything of 0, we don't get a value. So that, in effect, turns into a vertical asymptote. But knowing what value that is that makes that expression that we're taking the log of 0, that's a useful thing as well. So we'll have 3 basic pieces of information that we can just graph just about any logarithmic function without fussing too much about it. So we can see here this is an increasing function. It's concave down. We're going to be talking about derivatives of the logarithmic functions today, so you'll be able to see why that's increasing and concave down. Our domain, of course, is 0 to infinity. The range is going to be negative infinity to infinity. So those are kind of the important features to remember about any graph and any graph of the log function. Okay, so basically when we were transforming them, remember we had this way that we represent it where we have h and k, where h moves everything to the right and k moves everything up. Oops, it's a little fast. And so the same thing happens with our log functions if we use those 2 things. So let's say we have this function g at x equals the log base 2 of x minus 2 plus 3. So what we want to do to look at this is to say, okay, the vertical asymptote, where is that? Right now it's going to be at x equals 2. And how do we know that? Is that we set this expression that's inside the parentheses to 0 and we solve for it. The domain of this thing is going to be x minus 2 has to be positive, remember? So we're going to set x minus 2 as positive and solve for x, and we have x is greater than 2. The points that we get from the intercept, remember that when this expression equals 1, we have log base 2 of 1, which is 0. So we're going to set x minus 2 equals 0, so we know x equals 3. And so when we set x equal to 3, we get 3 minus 2 is 1, right? So the log of 1 is 0, plus 3 is 3. So we now have this point 3 and 3. Yes?
Can you re-explain that, please? The point from intercept, why that's important and how we can find that?
Sure. So if we have, I'll refer back to the graph that we had before. What we want to do is we want to figure out, where the log of whatever expression we have, where this is going to be 1, so that will equal 0. Okay, so we're looking for, in this case, we have the log base 2 of x minus 2. When this x minus 2 expression equals 1, we're going to get this expression equal to 0. And that gives us a really convenient point. So if I say x minus 2, where does it equal 0? Well, we can solve for that. And so then when we have, not 0. When it equals 1, we can solve for that. So 2 plus 1 is 3. And so we'll have the log base 2 of 3 minus 2, because now x is 3, that part is going to equal 0. And so that's that intercept that we're talking about. We're just this function, but we also have to add 3. So we get to the point 3, 3. So when we stick 3, 3 in this, or when we stick 3 in this expression, we get 3 minus 2 is 1. So the log base 2 of 1 is 0 plus 3. So g at x equals 3 then. So that's how I get that point, because I know that's an easy calculation for me to do, and all I have to do is set it equal to 1. Now with the asymptote, we know that we have to always be positive, so we have to set x minus 2 is bigger than, x has to be bigger than 2. If it was less than 2, we would be in negative numbers in our log function, and so that's not going to work. Okay, so then we have this, and we also know that when we have log base 2 of 2, that's going to equal 1. So what we're going to do is set that expression x minus 2 equal to what we want to find. And so we know that when x equals 4, the log base 2 of 4 minus 2 is the log base 2 of 2, which is 1. And that gives us another easy point to calculate. Okay, so I'm setting this x minus 2, this expression that's inside the log function. I want to set it to 2, and so I know I have to have x equals 4 in order for this value to be 2. And so when I stick it in my equation, then I get 4 minus 2 is 2, so log base 2 of 2 is 1, plus 3 is 4, and so I have another point, 4, 4. So I have those 2 points, 3, 3, and 4, 4, and I also have the asymptote, because I know this isn't supposed to be 0, or it's not supposed to be 0 or less. So if I graph this now, I have my asymptote at x equals 2, yes?
If it was log base 5, would we set x minus 2 equal to 5?
To 5, yeah. So then you would have, then it would be 7, right? Because then you'd have log base 5 of 5. Okay, so we know the asymptote, the vertical asymptote is 2. We have 2 points, 3 and 4, and we know the general shape. The domain is going to be on the right side of the asymptote, and we know from these 2 points how this is going to work. So if we just connect the dots and extend it to what we know, we get a basic, graph. Now it's not overly detailed. Clearly we don't have the new value. It's going to be 2 point something that gives us the whole expression equal to 0, and there's other ways to find that. But at least for giving us an idea of how the graph is shaped and where it is, this is a pretty effective method. Okay, so let's talk about reflections now. If g at x equals f minus, or f at negative x, we get a reflection. If we multiply something, if we multiply x by something, we get a compression if x is greater than 1. And then we also know that we get a vertical flip if we just make it negative f at x, right? All the positive numbers become negative and vice versa. So we can still use all the things that we know. Here, if we have a coefficient on the outside, we get a vertical expansion. That's not a surprise. And the thing that we have to keep in mind is that the domain changes, because the domain is dependent on what kind of legal values we'll get inside this log function. And so if we change that by adding to it or multiplying or whatever, we'll get different values. And so we have to keep in mind that as we're doing translations, our domain changes. And that makes sense. If you have a restricted domain and you move the graph around or stretch it or whatever, you may end up with different values for your domain. Okay, so let's go over an example where we want to graph. Here is 3 times the log of minus x plus 1. Now we can overthink this, and we think, okay, how do we stretch a graph by a factor of 3? The way we're drawing hand-drawn graphs of of these logarithmic functions, it's hard to say, you know, how do you stretch a curve by 3 without having any benchmarks? So I'm still going to look for the same basic values that I had before, finding where's the asymptote, what's the number when the argument is 1, and when it equals the base. So we'll go through that. The vertical asymptote happens when we get a 0 in here, right? That's an illegal value in there if you want to speak legalities. So we'll solve for x here and we find x equals 1. So we have our vertical asymptote at x equals 1. All right, so the point from where this inside thing equals 1 will make this log 0, right? And so we're going to set, when does negative x plus 1 equal 1? Well, when we solve for it, we'll subtract 1 from both sides, and we have negative x equals 0. So at 0, 0, we have our point. So let's check that. If we plug it in, 0, we just get the log of 1, which is perfect, because that equals 0 times 3, and so we have that 0, 0. So it's always nice to, you know, plug it in to make sure you actually have the right value. And then the other thing now is we want to set this thing so we get the log base 10 of 10. So we want to set this negative x plus 1 to equal 10. All right, so we can solve it again, and we see that we're going to subtract 1 from both sides, and so we get negative x equals 9, and so multiply both sides by negative 1, we get x equals negative 9. So we have our point negative 9 and 3. So there's our asymptote and 2 points. So let's see how this graphs. Here's our asymptote, x equals 1. Okay, and I have a point 0, 0. Then I have this other point way out here. At negative 9 and 3. So this, you can see how it really suggests the shape of this thing, where it's going to come from down here, and it's going to go up to infinity through that point. And so our graph then will be like this. So now remember we talked about when we make the negative x, you know, the inside the log, if we make that negative, it flips it around this way, and that's in fact what happens. This whole thing swung around from, normally it goes up to positive infinity, but because we have negative x, it goes over here. Notice you didn't even have to think about that with these 2 points, because these two suggest real values that you get from your function, and they happen to be the easiest computed values, and they tell you plenty about where the graph is going. Okay, any questions at this point? Yes?
For the first point, you just said it equal to 1.
This point?
Yeah.
I had it equal 1 because the log base 10 of 1 gives me 0. And that's what I want to do. I want to see what happens when I have the log of 1, and that gives me, presumably the rest of the function is easy to calculate. And then the second point is, when does it equal its base? So this is base 10 because it's a common log. And so we just set the whole expression, and then we solve for x, and then we'll get it. Okay, here's one for you to try. Actually, we have a lot to do today, so let's try this one, and then we'll pass on this one for now, okay? So let's see if we can do that. Feel free to work with the person next to you to be able to talk it over. Okay, so we'll see. Here's the calculation for the asymptote. There's the calculation that takes advantage of the log base 2 equals, when the log base 2 of 1 will equal 0. This one is when it equals the base, so we have the log base 2 of 2. And so there's our points. And I think on the next one here, this is, the red one here is what we just graphed. So we have the asymptote is x equals minus 3. We have our negative 2 and negative 1 and our negative 1 and 0. And so we can see it comes out nicely like so. So So I'll leave it up to you to go through the second one. Here you'll see this is a base 10 log, so we're going to set the expression inside the log to 0, 1, and 10, and we'll get our asymptote, or 2 points, and then we can put them on our on our graph. And you can see that with an asymptote of 1/2 and then 0, 3 and -9/2 and 2, it really suggests quite strongly what the overall shape of the graph is.